Hi, thanks for joining this talk. I appreciate that you're choosing to spend your time, your next 45 minutes here with me. My name is Cora Iberkleid. I'm an advisory solutions engineer at VMware. And today I'm going to be talking about building production-ready images with confidence and ease. So the title of the talk is "The Image is the New Jar." I'm going to go through a brief introduction just to set the stage, and then I'm going to go over 3 different methods for building images. So as an introduction, the context of this conversation is, of course, building images. So what you see here is a flow that should be pretty familiar. You start with some source code and you build an artifact. So in the context of Java, for example, you would be building a jar file or a war file that gets stored on an artifact repository. And then that becomes your unit of deployment, right? That's the deployment artifact that you deploy to a development environment or a test environment or a production environment. And those environments are ones that have been prepared for the application specifically, right? So it might be a set of virtual machines with an operating system, a JRE, a specific application server or an app server or a web server, sorry, and maybe even some shared libraries or some configuration. So with Kubernetes and generally container management systems becoming the de facto runtime platform, that paradigm is changing. And we are no longer expecting the target deployment environment to be prepared for our application, which means that all of those dependencies, the specific OS, the JRE, the app server, the web server, or the appropriate similar dependencies for any other framework you might be working with, need to be packaged with the application artifact. So in this case, for example, with Java, the jar file or the war file is no longer that deployment artifact. Instead, an image, which includes that code, plus all of the runtime dependencies, becomes our new unit of deployment. So the question becomes, how do we build this new deployable artifact? And how do we take on the responsibility of owning and managing over time all of the bits and pieces that should be packaged with the application artifact that previously were managed by a team further right on the lifecycle chain. So there are a variety of ways to build an image. I'm going to go over Dockerfile, Jib, and Cloudnative build packs in particular. And as we go through these, I would encourage you to keep in mind, as you compare them and look for pros and cons, keep in mind these factors for which we want to optimize, especially as you scale, or if you're thinking from an organization perspective, these factors become increasingly important the more images you're having to manage. So consistency of builds across applications or across development teams, the speed of builds, the efficiency of transferring changes over the network, for example. Security, of course, is always a primary concern. And this idea of governance, of managing, centralized management over what's going into your images, being able to manage that at scale. So let's start with Dockerfile. Now, some of the benefits of Dockerfile, of course, Dockerfile, it was introduced in 2013 with Docker. And so it's very widely used. It's sort of the de facto way to build an image. It was the only way for some years. And it's essentially a Dockerfile is a script that can produce an image. But really whatever goes into the script is up to you. It's a custom script that you write. Of course, there's specific commands that you use and the Docker daemon will execute. There's a few other backends besides the Docker daemon that can execute your Dockerfile. But essentially you're responsible for scripting how your image gets built. So because of that, it's of course very powerful and very flexible, and it can be used for any kind of application. So if we look at an example, this example is very simple. It establishes a base image that you're going to use with a JRE, in this case JRE version 8. That image in particular is available on Docker Hub. It's an openly available image. And then simply creating a working directory, copying a jar file that you would have built locally into the image and establishing what the command is for when this image is run as a container. So in order to execute this Dockerfile, you would, of course, first run your Maven package, since this particular script is not including the packaging of the application, and then simply call docker build on the files on the local directory. It'll find your Dockerfile by default, as long as you call your Dockerfile, and you give your image a name. And that's all. So that's a very, very simple Dockerfile, just to give you an intro if you're not familiar. But Dockerfiles can get more sophisticated, and it really is the responsibility of the author of the Dockerfile to do their research and understand what are the optimizations they can build into their Dockerfile, what security concerns need to be addressed in a Dockerfile. So for example, here you see that there's 2 blocks of code. So one is for building the image, and the other one is for the image that you're actually going to release into your production system. I'm going to go through this in more detail in a little bit later, but just to get the point across, that the responsibility of writing the Dockerfile and all of the considerations that go in it are in the hands of each Dockerfile author, which leads us to some of the drawbacks and limitations of Dockerfiles, which is really that all of the responsibility lies on you, right? So what base images do you use? What packages do you install? How do you validate that you wrote your Dockerfile correctly, that it's doing what you expect, that you're optimizing for use of cache and for speed? And then even if you do all of that correctly, Dockerfile still doesn't provide you with a mechanism to, for example, do any maintenance, right? So what if you're running your images and you need to upgrade the JRE or the OS itself? There's no system within Dockerfile that helps you execute that across an estate of images. It's also, every Dockerfile is its own thing, right? There's no central way to standardize. There's no formal way to share and ensure that the developers across your organization are reusing the same Dockerfiles or the same best practices within a Dockerfile, right? So there's a lot of reinventing the wheel, and you really end up with this hotbed for snowflakes where every Docker image can be different, or the images generated by each team can be different. And from an operational point of view, they're just a bunch of black boxes. You don't really know what's inside of them. So that brings us to Jib. So Jib is one of the tools that was created to try to solve some of these challenges with Dockerfile. And Jib is specifically for Java. Jib was introduced in 2018 by Google. And some of its benefits are that it's very simple. It doesn't require a Dockerfile. It doesn't use Dockerfiles, and it doesn't generate them either. It just has a different mechanism. It also doesn't require having a Docker daemon installed or having the Docker CLI installed, which is also sometimes makes things a bit easier. And it's integrated with Maven and Gradle via a plugin. So if you already have a workflow that uses Maven or Gradle, then it's very easy to incorporate Jib into that same workflow. It's fast. It includes some optimizations for build speed and for application startup. I'll give you a little bit more detail about that shortly. And it does what we call reproducible builds, meaning that if the inputs are the same application, the same build configuration, then it'll produce an exact same image every time. So I'm going to give you some examples using Maven, but you can check the documentation if you prefer Gradle. So the simplest way to use it, of course, is just to do a Maven, first compile, and then after you've compiled, add the build goal on the Jib plugin. And so you can see the full path to the Jib plugin there. When you use the build goal, what the plugin does is it builds the image and publishes it to a Docker registry. So in this case, you would give the image a name that included the coordinates to your Docker registry. As I mentioned, it doesn't require the Docker daemon, but if you do have a Docker daemon and you would rather just build to your Docker daemon, you can use the Docker build goal instead. And in that case, if you don't specify a name, it'll use the artifact ID and version as the default name of the image. And finally, there is an option to build as a tar file, which you can later load into your Docker daemon. So pretty straightforward. And it's a bit a bit of typing to type that whole Jib Maven plugin address. So of course you can just include that as with any other Maven plugin, include that into your POM file, or you can just add the goal of your choice into the package lifecycle, and then a Maven package would produce an image. Now, I think one really cool way to understand what Jib is doing is to look at this illustrative Dockerfile. So as I mentioned, Jib does not use Dockerfile, but this Dockerfile is found on the FAQ in the Jib documentation on GitHub. And it was an answer to a question, what would a Dockerfile for a Jib built image look like? So you can see here more or less what Jib is doing. So we'll go through some of the optimizations that I mentioned. So for one thing, you can see that when Jib produces the image, it's placing the Java application files on it in an unpacked manner, right? There's no jar file. And the benefit of this is that it's about a 30%, I think, speed improvement to start up a Java application that is exploded versus one that's a jar or a WAR file. So Jib automatically explodes the files in your Java application. It also, as you can see here, copies the files that comprise the Java application into the image in layers. Every copy statement creates a new layer in the image, and it does it in order so that the files that are least likely to change are copied first. So the dependency jars, so your Spring Boot jars, for example, all the way up to your class files, which is the code that you're writing. So that's most likely to change frequently. So that's the last layer that's created on the image. And that way, when you just change your own class files, the build is faster and also less data is transferred over the network to the Docker registry if you're publishing it. So that's another cool optimization that Jib is doing. It also uses the main class to start up your application. This is not as meaningful in terms of startup time as unpacking the jar files, but it's still a little bit of a lift. This idea of reproducible builds means that no matter where you build the image or when, you're going to get the same image ID. And for that, of course, you have to give up the timestamps, which would otherwise change the ID. Hence, the created date is not as meaningful, but the image ID is helpful because it is the same every time you build. As far as configuration, the configuration for Jib lives in your POM file or your Gradle build file. So here, for example, you can see a label being set. You can see the user being set to a non-root user. And you can also see a JVM flag that is enabling an agent that would have been copied over. You can see on the left-hand side, if you place any files in the source main Jib directory, then Jib will place those files in the image outside of the class path. And so that's one way you can get agents in there, for example. It's just sort of like the catch-all mechanism. So having understood all of that, we can identify some drawbacks and limitations for Jib. This idea that all of the config is baked into each build file, right? Your POM or your Gradle build file, that makes it hard to share the configuration or to standardize or centralize it in a way that more teams can take advantage of it across the organization. The catch-all, while it does enable adding agents, it's sort of a primitive config hook. It's still, you know, you're still responsible for the full configuration. And there's no mechanism for maintenance of upgrades and patches or standardizing, reusing, etc. Right? It's all per application, per POM file, per build Gradle file. And so over time, and especially at scale, the variance of the configuration and the nature of each image is going to change, and it increases risk because you also end up with a lot of variety across your estate that's hard to manage. And I mean, at this conference, it may not matter as much, but it is only applicable for Java, right? So you're going to have to find other solutions if you're also developing in other languages. So that brings us to Cloudnative build packs. Now, Cloudnative build packs are actually an evolution of an older technology called build packs that was introduced originally in 2011 by Heroku, and it was quickly picked up by Cloud Foundry. Cloud Foundry was under the auspices of Pivotal at the time, which is now VMware. But both Heroku and Cloud Foundry have been responsible for a sets of build packs for now 9 years. And build packs predate Docker, they predate Dockerfile, they predate Kubernetes. And what they did is to take an application and basically containerize it without actually using the container technology that is today Docker, and would run it on the either Heroku or Cloud Foundry platforms. So it was a predecessor to the containerization that we know today. And eventually over the years, these early generation build packs did make advances and incorporate the containerization technology that was evolving in parallel. And they did support multiple languages, but the broader mechanism was much more consistent, repeatable, secure, and auditable as compared to the Jib and Dockerfile approaches that we just went through. However, the disadvantages of these early generation build packs is that they were tightly coupled to these platforms, right? So if you weren't using Heroku or Cloud Foundry or a few others that were also supporting build packs, then you couldn't use build packs. They ran on the platforms. And even if you could have run those build packs, the artifact that they produced wasn't a portable container. So you couldn't have taken that product and run it, for example, on Kubernetes or some other Docker runtime. So there was this tight coupling going on. And beyond that, the build pack model was more of a monolith, right? There was a Java build pack, but it was a monolithic Java build pack. And it was difficult to modularize that. And so it really required a little bit of rethinking in terms of that, the model. And also there was no single API standard because Heroku started it, Cloud Foundry picked it up, but then they never really came together and said, let's establish a single standard that we'll both adhere to. And so all of these problems became especially notable as Docker and Kubernetes advanced. And so in 2018, Heroku and Pivotal again got together and said, given everything we've learned, given everything we know, let's make a new version of this idea that adheres to the newer container technology that's evolved. So they established this project called buildpacks.io. It became part of the Cloudnative Computing Foundation. And it basically fixes the problems of the earlier generations and also incorporates the latest technologies within containerization and results in a pretty powerful system. So in this case, the main concept, the main goal of the project is to define the process for turning code into OCI images. So they're not so much concerned with exactly how to deal with a Java application or a Node application, et cetera. But the Cloud Native Build Packs project itself is more focused on the orchestration of code into OCI images. So they establish a unified standard. They have, amongst other things, up an API to create platforms or tools that will produce images, and also an API for build packs. So for the side of the house that knows how to deal with Java, knows how to deal with Go or Node, et cetera, they've established APIs for each. So they're really enabling an ecosystem that will lead to different platforms being available and different sets of build packs being available. And this system also optimizes for fast rebuilds, minimal data transfer. And because it embraces all of the newest containerization technologies, it can also offer more advanced features like OS rebasing, which I'll describe in a little bit more detail. So that's all pretty good. So let's go over some basics. So there's two elements that you will be working with most directly if you are a Cloud Native Build Packs user. Those are a platform and the build packs. the platform is the tool that you're using, right? It could be a CLI, it could be a service running on Kubernetes, it could be a Maven or Gradle plugin, whatever the form is. It's a tool that implements the platform API provided by the build packs project, and it's the way end users can use build packs. And so the build packs are the modular components that contain the intelligence to turn source code into an image. And they do it in a way that is, again, manageable, auditable, repeatable, and reliable. So in order to make it easy for a platform to utilize build packs, the way that build packs are distributed is in an image called a builder image. And so that builder image, first of all, contains all of the build packs that you might want to use. The builder image itself serves as the build environment. So your application is actually going to be copied into that builder image, and it's going to build on that builder image. It includes a piece of software called the lifecycle, which is the generic orchestration code that any platform would have to execute in order to use any arbitrary set of build packs. So rather than have every platform implementation implement this lifecycle, the project decided we'll provide a reference implementation of this generic orchestration logic so that the platform can simply use that in order to use the build packs. So that lifecycle software is included in the builder image so that it's all easily distributable. And that builder image also contains a reference to a run image, because you don't want to deploy the builder image to your production system. Your builder image, for example, would have a JDK, whereas your run image only has a JRE, right? So you only want to release into production what you need for runtime. So, but the builder image does contain the reference to the run image. So all you need is that builder image. So speaking of the ecosystem that has been growing around this, from a platform perspective, the Cloudnative Build Packs project itself provides a CLI called Pack. That's the reference implementation for a platform. There's also a service called Kpack, which is a system that you install on Kubernetes. You configure it declaratively as opposed to Pack, a CLI that is imperative in nature. So Kpack is declarative in nature, and it can operate at scale and monitor many code repositories, build them, etc. For those who want that Jib-like experience or would rather adhere to their Maven and Gradle workflows, the Spring Boot supports the build packs ecosystem as well. So Spring Boot itself has become a platform, and so on. There's some others. And from a build packs perspective, of course, you have Heroku and Pivotal, the evolution of their original build packs. So Heroku has retained the name Heroku Build Packs, and the Cloud Foundry Build Packs have been rebranded under the name Paketo Build Packs. But so they sound new, but they are actually maintained and created and maintained by the same team that is responsible for the Cloud Foundry Build Pack. So it also includes all of the knowledge and experience that those teams have honed over the last 7 years. It's growing. I believe Microsoft also has one, and VMware Tanzu is a commercial superset of Paketo. So I'm going to show you a demo, mostly using Pack, but I'll also show you Spring Boot, and then we'll come back and talk a little bit about Kpack. So first, I promised to come back to that Dockerfile example. So here's that same Dockerfile that I showed you earlier, and I wanted to compare that to build packs. So in just broadly, in this Dockerfile, you can see that there's 2 blocks of code. Each one's called a build stage, and a build stage is initiated by this from statement. The from statement is the one that says which base image to use for the subsequent commands. So the first block here is, it's aliased as build, and all it's doing is starting with an image that has a JDK, it's installing Maven, and it's copying over the POM file, downloading the dependencies listed in the POM file, then copying over the source, and then running a Maven package. So at the end of this, we've got our jar file. And again, you can see that by the order of commands, the way things are split up between the POM file and the source, and doing the operating stuff first. Also, all of the multiple commands within this run statement. All of these things are optimizations and decisions that the Dockerfile author had to make in order to make sure that this Dockerfile was at least decent, right? I mean, there's things here that can be improved, but it's decent. And so it starts off a second build stage, and this is for we can call it the release or the run, with a base image that only has a JRE instead of a JDK. And really all it's doing is copying over the jar file that was created in the build stage. So it references the alias of the build that we assigned here. It copies that jar file. It makes sure that we're running as a non-root user, and then it sets the run command for when this image is initiated. Now, to make some parallels between build packs and Dockerfile, this Dockerfile, when you run docker build, this Dockerfile and the contents of the local directory, which would contain the application, are sent to the Docker daemon, and the Docker daemon executes the Dockerfile to produce an image. So we can, broadly make a parallel between that and the platform and the life cycle, and maybe even the builder base image. So the platform, much like Docker is the CLI with which you're interacting in order to use Docker files. For example, the pack CLI might be one platform choice that you interact with in order to use build packs. So that lifecycle has that generic orchestration logic. So maybe it's playing the role of the Docker daemon more than anything. And the base images include both the build image and the run image. So they would be the equivalent of these two from statements, the builder and the run image right there. And so all of these other instructions that go into either building your application or producing that, that final app, and the start command, for example, would be coming from your build packs. So the build packs you would use the Java build packs for a Java application, the Node build packs for a Node application. So for this demo, we're going to use Pack as our platform, and we're going to use these Paketo build packs as our build packs. And these Paketo build packs will include all of these three pieces, right? It's going to give us a builder image with the lifecycle and build packs, as well as our runtime image. And our platform is Pack. So I'm just going to go ahead and set this, use the pack set default builder command to set this particular version of the builder as our default, so I don't have to keep typing it. And before I actually build an image, I want to show you what you can glean about the contents of the builder using this inspect builder command that is also provided by Pack CLI. So let's inspect the builder. So you can see, let me start a little bit higher here. Okay, so of course we can see what version it is. We can see the stack, for example. This uses a Ubuntu Bionic stack for both the builder image and the runtime image. It gives us a little bit of information about the version of that lifecycle and what API versions it supports for both build packs and platforms. It tells us which run image it's referencing. And then we have the entire list of build packs that are included on this builder image, as well as their version, and a link to their homepage, which has the documentation for each one of these. And you can see here that some are Java, some are Nginx, and Node, etc., Go, .NET, etc. And so there's also some metadata included here that provides a detection order so that when you build an image from an application, the process of figuring out which build packs apply to your application are evaluated in this order specified here. So just a little extra metadata. So we can see anyway that this particular builder supports .NET and Go and Node and of course Java. So it's a good choice to have as a default builder. So now that we know that our builder will support our application, we can go ahead and build it. So all we have to do is call pack build. We're actually in the directory that contains our Java source code. So we can just, we don't have to specify the path. It'll just look in the local directory. We do give our image a name. You could add a tag, of course. And you don't need this flag, but I'm adding it because I've already pre-downloaded the builder. And I just want to make this a little faster. So just telling it to use what's available locally. So you can see from the output here that the first thing that it does is it figures out which build packs of all of those build packs that were included in the builder, which ones to use. And it's identified that it wants to use 6. And you can see by the choice of build packs that it's automatically determined that we have a Spring Boot, Maven, Java build pack. And this is the order in which it's going to apply these modules. So this is the first time we're building this image. So this analyzing and restoring phases here are not doing anything quite yet. They will reuse, they will enable optimizations in terms of reusing cache later. Sorry, it's downloading all the Spring Boot stuff, so it's scrolling and making my screen a bit jumpy, but let me go back here. So the first thing that it's doing is installing this. So in the building stage, it actually applies every build pack in order. So you can see, for example, that the Liberica build pack is run, which downloads the JDK and the JRE. The default version is 11. Here it's giving us all this extra information about environment variables that we could use to configure. Then the Maven build pack takes over and it starts downloading all of our Spring dependencies. Let's scroll past all this. And after that, it decides what is the process type and what is the launch command that it's going to use. Finally, it can do some Spring Boot specific stuff, including, as you can see here, creating slices from layers. So this is similar to that Jib behavior that we saw, where Jib separated the application files in terms of the Spring Boot dependencies and then snapshots, et cetera, up until the class files in order of likelihood to change. So with Spring Boot 2.3.0 and higher, you have the same capability. So you can see here that it's also organized the application files in order. So Spring Boot dependencies first, then loader ones, then snapshots if you have any, and then finally your application files. And it creates a separate layer in the image for each of these. And then in the end, it does the exporting of the pieces that you need, the layers that you need for runtime into the run image. And it also creates a separate cache for the things you don't need on production, like the JDK, for example, so that your next build will be faster. So there's a lot of optimizations built in here. I can point out a few more later, but for now, let's look at the Docker images, and you can see that here is the image that we just built. Now, that app file layering that I showed you here, the fact that it's able to organize the files in terms of dependencies, the loader, the snapshot, and the application, that happens because I enabled layering in my POM file. So I'll show you the first 60 lines or so of my POM file. So first of all, you can see that I am using Spring Boot 2.3.0 or higher. And then within the Spring Boot Maven plugin, I've simply added this configuration, which says layers enabled is true. And with that, once I use Cloudnative build packs, it'll automatically organize my files and create different layers for each. And of course, it is also transferring them as an exploded jar file. So the same optimizations we saw with Jib, they're all included here and more. In fact, we can use this tool Dive to actually look at the layers inside of the image. Dive is a pretty cool tool if you haven't used it before. So I'm just gonna quickly tab over to the right, which shows me layer contents, and hit Control U So I can only see, I only want to see what changes on each layer. So as you go down, now I'm going down on the layers on the left, and it'll just show me the new things on the right-hand side. So for example, here's still some OS stuff. And finally, we get to the Paketo build pack is adding, here's the JRE, for example, the JVM killer, etc. And then when we get here to this layer, you can see here is a layer of the basic Spring Boot file. So these are probably not going to change very often. So that's an 18 megabyte layer that's created separately. And then the loader files, there's no snapshots. And then finally, this 10 kilobyte layer is my actual code. So now if I just change my code, I might be just transferring up to 10 kilobytes or so, right? Rather than transferring 18 megabytes, which would be the case if it were just a jar file and everything were packaged together. So that's pretty cool. This tool is pretty cool. Okay, so another thing I want to show you is customizing. So far we've built images with all the defaults. But what if you want to add your own module, your own build pack that's specific to something your enterprise needs to do, or you want to set some kind of configuration that's different from the defaults, right? So you could write your own build pack. I'm not going to go too much into the details, but I'll show you the structure of a build pack. So basically you would have a configuration file, a TOML file. And in this example, we have a build script and a detect script. So that gives you a bit of a hint as to the build pack's API, right? It does first it has a detect. So it allows the build pack to say yes or no. I do have to execute on this code, or I'm not applicable in this situation. And then if the detect returns yes, then when it comes time to execute this build pack, this build script will be called, and the build pack can do whatever you want it to do. So we'll include this custom build pack in our next build. And what we're going to do is, the way you include it is just to include it with the -- build pack flag. But we want to do it in addition to the builder build packs, right? And we can decide if we want it to run before or after all the other build packs. So in this case, we're deciding we want to run the the builder build packs first, and then our custom build pack. And then we're also going to take advantage of the fact that the Java build pack is configured via environment variables. And so we're going to add this BPJVM version, and we're going to change it from the default 11.star to 14.star. So we're making two customizations, and let's go ahead and rebuild that. So you can see already in the detection that our custom build pack is included. You can see that it's taking advantage of cache. At this point, it's downloading JDK 14 because that's the thing that we changed, so we can't reuse that particular layer. It'll download the JDK as well as the JRE. And then here we also have an opportunity to see some of the, like for example, the Maven arguments. You could also configure that. By default, it does a Maven skip test equals true and then package, and so on. And so here it is, it ran our, well, first of all, here you can see that it did notice that our BPJVM version is 14, right? It downloaded 14. And it also ran our Hello World build pack after all of the others. So it did our customizations and created a new image, which is great. And what happens though if you don't have access, or if you don't know what command was run to generate an image? Can you still know what went into the image? And so this is a great feature for security teams, for example. There is a pack inspect image command, just as we saw the inspect builder, you can also inspect images. So this command produces a bit of JSON that I'm actually going to show you via the browser. It's a bit easier to read. So even if you didn't know how the image was built, you could always grab the image, run the inspect, and I can see, for example, here that the JDK is version 14, the JRE is also version 14. I can scroll to the bottom, I can see that my sample Hello World build pack was run, version 001. I can even see the Spring Boot build pack actually includes all of the dependencies that went in from the POM file. So I can see here, for example, I know I'm using 2.3.1 of Spring Boot, but I can actually see all of the different libraries that went into my application. So from a security, transparency, inspection perspective, this is pretty powerful. The other feature I want to show you is rebasing. So in this case, if you imagine, for example, a situation like Heartbleed or Spectre, and you don't want to necessarily rebuild your application or rebuild your image, you just need to swap out the operating system. So this feature is very powerful. So it's basically, instead of a build, you use a pack rebase instruction and reference, there's a few different ways to do it, but this is one. You can reference the new image that would have the fix for the vulnerability. And in this case, it simply does a swap. So really what it's doing ultimately is it updates the manifest for the image. And the manifest is pointing to the different layers. And it just changes the pointers to the OS image. And so that just took a few seconds. So that's the fastest OS patch application I've ever seen. And so now we have the new idea of the new image with a new operating system, but everything else is exactly the same and wasn't rebuilt. Now, if you like that JIB experience, Spring Boot, as I mentioned, is an alternative to the pack CLI, and it also offers integration through Maven and Gradle plugins. So in this case, for example, I'm going to use the Spring Boot build image plugin with Maven, and you'll see from the output, first it does a Maven compile, and then you can see here, now the output starts to look the same as we saw before, where it detects, it does 5 of these build packs are identified, and it goes through the same process. And you can see here the JVM kill agent, for example, the somewhere here it should be the memory calculator that was inherited from the Cloud Foundry build packs, which is a really great feature. And it also does the layering of the application files, and ultimately you end up with the same image. And in this case, the main difference is it actually defaults to the artifact name inversion. So you automatically get this Hello Java 100 version. Now, just to go back to the slides quickly. I just want to recap that rebase operation. So if you have an image that's pointing to layers added by the build packs that are sitting on the add to the run image base layers, if that image is detected to have some kind of vulnerability like Heartbleed or Spectre, then you would rely on the build packs, for example, Paketo, to provide you a new image. And once that new image is available, you can call this pack rebase operation. And really it's just taking the manifest file that represents the image and pointing some of the layers to the new run image, but the old pointers stay the same. So it's really quick and very simple. And this is the last platform that I wanted to mention, which is Kpack, which you install on Kubernetes, and it polls your source code repository, and it also polls the builder, the run image and the builder image. And if any of those change, it automatically does a rebuild if the source code changed, or if the build packs changed, or a rebase if only the run image changed, and it updates those images on your Docker registry. So that's extremely powerful at scale. And then all you have to do is apply those Docker images to your Kubernetes clusters. So that's pretty cool as well. So just to recap the benefits of Cloud Native build packs, they're really easy to use. They're enabling an ecosystem of platforms and build packs, and the platforms are really tuned to different use cases. There's a lot of optimizations built into this system, advanced features, and the modularization of build functionality. It's very useful for plugging in custom build packs or build packs that are specific to APMs, et cetera, scanners. Of course, all of the transparency is key. And the Paketo build packs are, as I mentioned, an evolution of Cloud Foundry. They're chock full of best practices. They support multiple languages. They're actively updated. There's been a lot of investment in modularizing these, and the configuration is really straightforward, either through a build pack YAML or environment variables. So that's really all I have. Please feel free to contact me with questions. And it's been a pleasure. Thanks for joining this talk.